Physics 065 Cambridge IGCSE Topic 5 Forces and Matter. So let's begin. So we'll just start off by defining forces on solids. Okay, there are two main points you need to consider before we begin. Okay, when forces are applied to materials, their size and shape can change. Less springy materials become permanently deformed when forces are applied. Okay, so now we're going to come to the main part, which is we're going to be talking basically in this whole section we're going to be talking about springs and extensions and how to basically perform calculations on springs. Okay, so stretching springs is basically our main topic for today. Load. Load is the first definition, a force or usually a weight or mass that stretches an object, which is a spring. So basically imagine you have a spring and you apply a weight to it that will stretch the spring. That is a load. Okay, so let's say like you have a spring here, okay, and you just apply a load here of, let's say, 5 kilogram, and this is just going to stretch the spring downward. This is the load that we're talking about. Okay, anything that just stretches a spring, anything heavy like a mass or weight, that will stretch a spring. Key points: as the load is increased, of course the spring will stretch more and more, and the length of the spring will keep increasing. If the load is increased too far, so if you use a load that's too heavy, the spring will become permanently stretched and deformed. This means that if you're using a load that is so heavy on the spring will become permanently deformed and it will not be able to go back to its original length anymore. Okay, if the load is increased within the range, then when the load is removed, the spring will return back to its original length. So basically when you have a spring, okay, it's very simple. You have a spring, you apply a load. If you apply a load that is too heavy, the spring will stretch too much, it will become permanently deformed, and it will not go back to its original position. If you have a spring, you apply a load, and you keep increasing the load, but you keep it within the range, you don't increase it too far. When you remove the load, the spring will return back to its original position. Okay, so as we can see in the diagram here, okay, we have a spring here, okay, and this red line is showing us what is the maximum capability of the spring to stretch. Okay, so we are at level 1, level 2, level 3, level 4, at level 5. As you can see, up till level 4, everything is okay. If you remove the load from level 4, the spring will return back to its original position. But if you remove the load, if you increase the load till level 5, and from here, if you remove the load, the spring will not return back to its original position. Why? Because it is permanently deformed now. You have increased the load too much, now it cannot go back to its original position. It is deformed. Stretching springs. Okay, so extension. Extension is the change in length, delta L, of a spring when forces are applied on the spring. Okay, so basically we have, first of all, we have two type of forces on a spring: extension and compression. Extension means to extend the spring, make it longer. Compression means to make the spring smaller. Extension are referred to as tensile forces. Compression are referred to as compressive forces. So a key point is that if you double the load, the extension is doubled, but the spring will not become twice longer. Okay, the formula of extension is very simple. Remember, anything that has delta, okay, delta means final minus initial. So delta of velocity, final velocity minus initial velocity. So delta of length will be length minus length 0. Okay, new length minus original length. Change in the spring length is delta length, new length minus original length. Okay, so and I could use this example over here, this example. Okay, but I'm not really going to use this. I'm going to go back to the previous example to explain it from here. It's going to be much easier over here. So let's say the initial length of this spring is 2 meters. Okay, and the extended length, let's say at level 4, the length is, let's say, 6 meters. So we know extension by x is equal to delta L. Our delta L here will be L minus L0, new length minus initial 6 minus 2 is equal to 4. So extension is equal to 4. that is basically the idea, okay? So basically take the final length, take the initial length, subtract the final from the initial, that's your extension. I didn't take this example because it was a bit complicated. Experiment to measure the spring's extension. This is not really required anymore in the syllabus for 2023 to 25 exams, but I'll still go through it. So basically set an apparatus as shown in the diagram. So as shown in this diagram, set an apparatus like this. Attach a single mass to a spring, okay, and position it against the ruler. Just measure the spring, okay, the length of the spring. Then add further masses and keep measuring the new positions. Continue until you have added 7 masses. Okay, repeat the experiment 3 times for validity. Take the average after the measurements. Find the force, okay, which is the mass on the spring, and the extension. Then subtract the original length from each subsequent positions. After that, you plot an extension load graph. And that is what we need to focus on, okay? So before I come to the extension load graph, let's first understand Hooke's experiment. Robert Hooke, I don't mean the singer Robert Hooke, I mean the scientist Robert Hooke. Robert Hooke was a scientist who experimented, executed an experiment on springs, okay, which was, so as you can see in this table here, we have mass per kilogram, mass in kilograms, length in centimeters, extension in centimeters, and weight in force per Newton, okay? So what did he do? As you can see in the first level here, he took a spring with no load, okay? Mass was 0, okay? The initial length of this was 18.0. So of course the extension is 0. The weight applied, the load was also 0. After this, what happened? He increased the load to 1, okay? So weight is equal to mg, okay? Weight is equal to mg. M is equal to weight over g, okay? So he increased the load to 1. The mass became 0.1 because weight is 1 divided by g, mass is 0.1, okay? The length increased to 19.2. So what is the extension? 19.2 minus 18.0, 1.2. Then he increased the load to 2. So mass is equal to 2 divided by gravitational field, which is 0.2. The length increased to 20.3. So what is the extension? 20.3 minus 18.0, 2.3. Then he just kept increasing it all the way to 5. Okay, so for example at 5, what is the mass? Mass is equal to 5 divided by gravitational field, 0.5. Length was 25.1. Extension, 25.1 minus 18.0, 17.1, okay? So the extension here are dependent variable, the variable to be measured, which is always on the y-axis. Our independent variable that is constantly changing is on the x-axis, which is our load. So now we plot our extension load graph. So basically, this is Hooke's stable graph. He plotted the points from the experiment on this graph. Okay, so what we found out is that the extension and load, okay, at first up to 4 Newton, which is here, okay, the graph slopes up steadily, which is a straight line through the origin, linear graph. The spring can return back to its original position. Why? Because the extension is directly proportional to the load. As the load is increasing, the extension is increasing, okay, and it's forming a straight line. But after 4 Newton, something happened. The graph started to bend towards the extension. Why is that? Or towards the force applied. Why? Because there's something called the limit of proportionality, and the graph has exceeded the limit of proportionality, or the spring, okay? So after 4 Newton, limit of proportionality has been exceeded. The graph will curve towards the x, okay? The load is so great now, the spring has become permanently deformed, and it will not return back to its original position. So before it was in the elastic linear region, graph is increasing steadily, okay, directly proportional. Now it's in the plastic region, deformation has occurred, it will not return back to its original position, okay? To define limit of proportionality, it is basically the point at which the graph begins to curve, meaning at limit of proportionality, the spring is stretched beyond this point and it will become permanently deformed. When the load is removed, it will not return back to its original position. So after experimenting this and plotting the graph, Hooke made his law, which is known as Hooke's law. Hooke's law is the force applied on a spring. The force applied on a spring is directly proportional to its extension provided LP is not exceeded. So the force applied to a spring, as you can see in the graph, is directly proportional provided LP is not exceeded. Once you exceed LP, the force is not directly proportional to the extension, and Hooke's law is not obeyed anymore. Hooke's law equation depends on the stiffness of the spring, also known as spring's constant. Spring constant is by symbol K, which is how much force is needed to extend the spring a unit distance. Basically, force per unit extension. K is equal to F over X, force per unit extension. As you can see by the formula triangle, K is equal to F over X, F is Kx, and X is F over K. Some quick facts: metal wires obey Hooke's law. Hooke's law is only associated with the initial linear straight part of the load extension graph, not the bending part. Objects that obey Hooke's law return to the original position after being stretched because it's directly proportional. After limited proportionality has been exceeded, objects will no longer obey Hooke's law and will not return to the original position. After limited proportionality, length is increased so much that the spring will be lower and K will decrease to form or become a new spring. Basically, after limited proportionality, it is a completely new spring. Okay, it's not the same spring anymore because limited proportionality is exceeded. The extension is not directly proportional to the load. We have three types of graphs here. A load extension, we have two types. Where when force is up and x is down, the slope is k. When x is up and force is down, slope is k over 1 slope. Force and length graph. Force is up and length is down, slope is k. Mass extension graph. Mass is up, x is down, slope is k over gravitational field. And k is slope times gravitational field. Factors affecting the spring's constant. So first is the history of use. Of course, how much has this spring really been used? Okay, but this one's not really that important. The three main one is the type of material the spring is made of, which will depend on how easily it is permanently deformed. The thickness of a string directly proportional. More thickness, okay, there's higher elasticity. Length of the spring inversely proportional. Less length of the spring, more spring is constant. Rubber, I'll be skipping that for now. Stretching springs, okay. What are two reasons that Hooke investigated springs? Why? Because springs are used to make weighing machines, and spiral springs are used to make clocks. As you can see in this diagram, this is a normal spring. This is a normal spring. This spring has exceeded limit of proportionality, which will not return back to its original position. Connecting springs. So you can connect springs in two ways. We will go through both of them in a brief: series and parallel. Series is when you connect the strings up and down. So basically this is K and X, constant and extension. The total stiffness of series is Fk over 2. Total stiffness is less than a single spring. If the force is applied in a system, it will extend double the extension in a single spring, okay? In parallel, it's a bit different. In parallel, you're connecting them side by side to one single load, okay? So total stiffness is 2K because of both in one single load. Total stiffness of a system is quarter that of a single spring. If force is applied, it will extend half the extension in a single spring, and the same force is applied. And that was basically it for topic 5 in Physics 0625 Cambridge IGCSE.